positive charge of 2E. So E just stands for the fundamental charge on a mass of 6.6 and a mass of 6.6 kilograms. Okay, so we got alpha particle. We know the charge. We know the mass. And we need to find the velocity. And we'll say it at state B for an alpha particle which reaches the negative plate of a parallel plate apparatus with a potential difference of, so we're given the potential difference. Okay, so we have a parallel plate apparatus. So here's the positive. Here's the negative. So our field lines extend from positive to negative. So we'll draw our field lines here. In a parallel plate apparatus, the field lines are all parallel. Because they're parallel, the density of the field lines is constant at all points in the field. So we have a field of constant strength. And here's that alpha particle, it's a positive particle. And we know that it's going to accelerate, repelled from the positive plate, attracted to the negative plate, and it's going to hit that negative plate. So here's state A, alpha particle at positive plate. Here's state B, alpha particle at negative plate. The particle starts from rest and then hits plate B with an unknown speed or velocity that we need to calculate. All right, so this is a we'll just do part A, we'll leave part B to you guys. It's a conservation of energy style problem, so we can draw those bar graphs. So let's draw the bar graph for state A. So what types of energy are acting in the system? What types of energy do we have present in the system? We have electric potential. What else do we have?
Kinetic.
Kinetic. What else do we have? What about gravitational? Well, it's got some mass to it. Do we consider gravitational? Who votes yeah, we should consider gravitational? Who votes no? Okay, why no?
Because the mass of the test charge is like really small, so we just don't.
It's so tiny that we could have it in there. This thing technically, if you know, this is down. This thing technically is going to follow a bit of a arc, like a projectile, but the y component is going to be so small that it won't even matter. So yeah, the answer is they give us the mass, but why does the question even give us the mass? What do you think? Why is it giving us mass if we don't even need to consider gravitational? So that's right, we're going to need it for our kinetic term. Okay, good. So there's the total energy. So let's draw our graphs here. So we start off with full mechanical energy, and all that energy is stored in the field at that point. Now the analogy here is if you have an object and you raise it above some reference point in a gravitational field, all the energy now is stored in the field. The energy is stored in the Earth chalk brush system, or you can also think of it as being stored in the gravitational field. Now upon release, it falls, and that's exactly what we do here. So at some point before the question started, we pulled this, this alpha particle to the positive plate, just like I lifted up the eraser, and now we're going to release it, like we release the eraser, we release the alpha particle and it snaps back to the negative plate. So really no difference. So when you think of these electric fields, just always think of the gravitational equivalent and how easy that is. You've been doing it for 2 years now, right? Well, 2 semesters. Okay. Now at state B, we've got a last electric potential, kinetic, and our total energy. We get conservation of energy. And now, at the negative plate, how much energy is stored in the field at this point? Once that alpha particle reaches the negative plate, exactly where it wants to be. How much energy is stored in the field?
The entire bar of kinetic is full.
That's right. So we have no energy left in the field. Okay. So now, as is usual with energy problems, you just compare the states. So energy at A equals energy at B. So all we have at A is our electric potential, and all we have at B is our kinetic. So this would be the Q, the charge of the test charge, which is 2E. You guys can put that in after. Times our voltage, electric potential difference. This equation will give us the electric potential energy at that point. This equals 1/2 mVb squared. Call that VA because it's the electric potential difference when the object is at state A, when the alpha particle is at state A. So we know Q, we know electric potential difference, we know the mass, we solve. Yeah, so there's state A. We could also define something in the center as state C. Let's go on to part B, why not? So it says if it started from rest at a point halfway between the plates.
We're given all these equations on the test.
You will be given, let's go through and explain what you're going to be given.